All right, we're going to stay in space for one more talk. Our next speaker is Dr. Michael Johnson, an astrophysicist at the Harvard Smithsonian Center for Astrophysics and Project Scientist for the Next Generation Event Horizon Telescope. Michael is a current colleague of mine. He's an exceptionally accomplished scientist and truly one of the most genuinely brilliant people I've ever been around. Michael has been one of the key science leaders of the Event Horizon Telescope, a collaboration of over 300 people all over the world that came together to create the first image of a black hole in 2019. It took a telescope the size of the Earth to do that, and you'll hear more about that in a minute. He's a prolific scientist with over 100 publications to his name and a dedicated mentor. And there aren't many people who can say they've been on a list of recognizing the top 50 accomplishments of a given year. This was in 2019, the Bloomberg 50. Let's see, on that list you've got Rihanna, you've got Jon Stewart, and Michael Johnson, along with the other leaders of the EHT team. But I don't know, Michael, I was going through that list of the other 50, and the Popeyes fried chicken sandwich is also on that list. I don't know what it says about the list, but it does really make me want to try one. All right, so let's welcome Dr. Michael Johnson, a scientist as accomplished as a Popeyes fried chicken sandwich is delicious. All right.
Thank you so much, Karen. Can everyone hear me okay? Yes, okay. So over 100 years ago, Einstein published his theory of relativity that we just heard about. And one of the most striking predictions of this was the existence of black holes. And these are objects where you compress them down small enough that the gravitational force becomes so strong that nothing can escape, not even light. So, we heard that Einstein sort of thought of this as just a mathematical curiosity. He didn't take it seriously at all. And for decades, scientists who believed in black holes were actually mocked. But gradually, scientists began to believe that not only could black holes exist, but that they were common in the universe. So the story I want to tell you about today is the story of taking the first ever picture of a black hole. Now, how can you take a picture of something that doesn't emit any light? It turns out you can take a picture because black holes cast a shadow. So here's an example showing light as it's passing near a black hole. So because black holes actually curve the space-time, as light comes near it, it gets bent. And so if there's lots of material that's emitting light near a black hole, stuff that passes too close to the black hole gets captured, stuff that passes near gets bent, and further light doesn't get affected very much at all. And the net effect of all of that is that black holes cast a nearly circular shadow if they're surrounded by this emitting material. So the first scientist who calculated what the size and shape of the shadow would be was actually a mathematician named David Hilbert. So he published this in an article that he modestly titled "The Foundations of Physics." And so Hilbert was actually using this formula that had just been derived by Karl Schwarzschild. So Karl Schwarzschild, he was stationed on the Russian front in World War I, and while he was there, he was doing these calculations. And he sent this lovely note to Einstein. He said, "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this, your land of ideas." So this incredible pursuit that these are scientists, they didn't think black holes existed, they're just doing this for fun. So the next thing that happened was that scientists realized that black holes weren't just defined by how much stuff was in them, their mass, but they could also be spinning. And it turns out that if you have a spinning black hole, it shrinks that event horizon a little bit, and it shrinks the shadow just a tiny amount. So this is an incredible prediction. It's saying that all these black holes that might exist in the universe, they have a very similar shadow. And again, these theorists, they weren't doing this because they thought it was relevant. They were doing it just because they were curious. So Bardeen, who's the one who did these calculations, said it's conceptually interesting, if not astrophysically very important, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect. So why were they so, why did they think this was impossible? It's not because black holes are black. They actually power some of the brightest regions in the universe. The reason that they thought this was impossible is because black holes are extremely small. And so to see a black hole actually requires a telescope that's thousands of times sharper than even something like the Hubble Space Telescope. And doing that requires an entirely different type of telescope called an interferometer. So just to put this in context, when you go out and gaze at the night sky, you're able to see stars and planets and things like that. And how sharp you can see depends only on two things: the size of your eyes, and also the wavelength of light that you're looking at, the color of the light. So big telescopes can see smaller things, and looking at bluer light allows you to see finer features. Now, interferometry is different. The magic of interferometry is that you're able to combine different telescopes to make an image where the sharpness of your image doesn't depend on how big the telescopes are. It only depends on how far apart you can place them. But this magic comes with a price. And that price is that every pair of telescopes just samples one spatial frequency of the image. So these telescopes, they don't spit out an image like an ordinary telescope. They're sampling this odd information. And one way to think of it is if the image were a song, every pair of telescopes would hear just one note of that song. So to see the whole image or hear the whole song, what you need is many different baselines, many different telescope combinations, both long and short, and then you can put all that information together to get the picture. So this is kind of an odd concept, and I wanted to give you a sense of what it's like to be an interferometer. So what I'm going to do is I'm going to play a song for you, and I'm going to let you hear it as though you were an interferometer. So we're going to start with just two telescopes. Two telescopes have just one baseline, so you'll only hear one note of the song. Then we're going to add more and more telescopes, and I want you to just raise your hand when you recognize the song that's playing. So here we go. So we'll start off, you hear just the one note from the two telescopes. Now we're going to go to four telescopes, so you're hearing 6 notes. So just raise your hand when you think you recognize the sound. So that's how interferometry works. And the amazing thing is that you can be missing most of the notes, and your brain fills in all of that information, and so you recognize the song even when you only have partial coverage. So pulling this all together, this is the Event Horizon Telescope. It's not one telescope, but it's a set of telescopes all over the world that are acting together as an interferometer. And because we're letting algorithms fill in all that information just like our brain, it's like having an Earth-sized telescope where most of the surface is missing, and we use algorithms to fill in that missing information. So even after we built this, though, I want to give you a sense of just how absurd it is that it actually works. So if you took all these telescopes and you point them at the brightest black hole in the sky, and you observed continuously for a year, the total amount of energy that all of them receive together is about the same as if you pop a small soap bubble. So in order to take that tiny, tiny amount of information and actually convert it into a picture, what we do is we swallow huge amounts of data. So we actually record petabytes of data across all of our telescopes, and we use that as our way of achieving enough sensitivity in order to make a picture of a black hole. Okay, so to put this in context, what we did in 2017, we took all these telescopes, we connected them together, and we pointed them at the M87 galaxy. So this is an enormous elliptical galaxy. It's about 50 million light years away, and it's tucked in between the constellations of Virgo and Leo. Now, we're going to zoom in here and see what all these different facilities see. These are actual astronomical images. So the first thing is what the Hubble Space Telescope sees is just this kind of blurry ball of stars. So it actually can't see much of anything. But we can use interferometry to get a sharper view. So this is with radio interferometry, and we see that a jet takes over the picture. Then we can look at higher and higher frequencies, which was developed over decades of work, and it becomes more and more translucent until we get to 230 gigahertz, and this is the first ever picture of a black hole that was taken by the Event Horizon Telescope and published in 2019. And this is hot gas around the black hole. It's heated to about 100 billion degrees, and that's shining brightly, and that hole in the center is where an enormous amount of mass is concentrated. Now, after the first time I saw this, I just kind of walked around in a daze. And it's hard to convey just how ludicrous this situation is. So to put this in context, if you want to make the Earth into a black hole, you have to compress it down so it becomes, the gravity becomes stronger and stronger. So it turns out that if you want to make the Earth into a black hole, you would have to compress it down until it was about an inch across. You could hold it on your finger. For comparison, this black hole is so large it would engulf our entire solar system. It has about 6 billion times as much mass as our sun. So this is a striking number, and it's even surprising to people who work on this. So as a fictional example, many of you might have seen the movie Interstellar. So Interstellar features a large black hole. In fact, it's so large, the black hole is just called Gargantua. So it turns out this fictional black hole Gargantua is 70 times smaller than the actual black hole that we saw in M87. So yeah, nature is just always surprising us. So this was only possible through the work of a global collaboration. It's hundreds of scientists spread over all the world, creating, deploying equipment to these facilities, developing algorithms, running these observations, and doing all the science. And really the best part of it was being able to share it with the world. Most science that we do requires a PhD just to understand why it's interesting. But this is science where a 6-year-old is excited for the same reasons that I am. And so it really did inspire lots of people, and it's a joy to be able to share it with you today. So thank you so much, and thanks to Garrett for organizing.